All right, good afternoon, BWSI. How are we doing today? Awesome. Well, I am very pleased to introduce our seminar speaker this afternoon, Dr. Olga Mikulina from MIT Lincoln Laboratory, where she is an expert in high-speed laser communications. Today, she's going to talk about how she and her team worked to build the optical communications payload on the recent Artemis 2 mission, which enabled the Orion spacecraft to transmit high-definition video and scientific data back down to Earth at unprecedented speeds. So let's give her a very warm welcome.
Thank you. Thank you. Thanks for coming. I'll be giving my presentation about the optical communication, the project that we did in the lab. And I just want to talk a little bit more about the human space exploration and how communications have been a very important tool for the science, for engineering. And let's start from history of the human space exploration. In 1961, the first human in space, Yuri Gagarin, flew around the Earth in low Earth orbit. And the only way to communication to the ground was a very high frequency radio link that was picked up by the ground station that were located in a line of sight. When he went away around the Earth, the communication was stopped. The telemetry was transmitted through the high-frequency link, and it was picked up by all the ground stations in Europe, United States, and the whole world get inspired by having a human in space. 1965, there was first EVA. Who knows what EVA is? What? That's right, right. That's when the human astronaut gets out of the spacecraft and goes in open space. And so for that action, there was also a radio link. There was a separate radio link for his voice. There was a separate radio link for telemetry from the sensors. And then there was also slow scan television link that transmitted it indirect. Following that, there was many exploration, 1977, Voyager, 69, 72, famous Apollo program that brought people to the moon. It was 11 missions. It brought multiple astronauts on the surface of the moon. And there is a space shuttle era, 1998, International Space Station continuously hosted humans, multiple groups of people on low Earth orbit. Then 22, Artemis 1, 26, Artemis 2. And as spacecrafts are getting more sophisticated, we have better cameras, better telescopes. The need for sending data gets more and more pressing. So I want to show an example of the Voyager mission. The Voyager mission sent out 2 probes to the deep space in 1977. One probe visited Juniper, and another one visited Uranus and Neptune. And 2 different probes, both of them had a 3.7-meter antenna, and the antenna power was 23 watts. The signal was very low. It only can transmit very low rate telemetry. So like as of now, these probes are still in space, and I think Voyager, one of the Voyager still establishes regular communication to the Earth. And like it's pretty amazing, the vision of people who were in 1977 sending the 2 probes to outer space. And as of recently, they've crossed the interstellar boundary, and so they went beyond the solar system. And this is the type of the receiver that needed on the Earth. NASA supports Deep Space Network system. These are 3 different antennas that are located on the ground. They're about like 120 degrees longitude. spread. One is in California, one is near Spain, Madrid, and another one is Australia, Canberra. And from the Voyager, the power of the received, so like I said, the transmitter power was 23 watt, and the power detected on the sensors was 3 to the 10 to the minus 19 watt. So it's a very low signal, and at that power level, you can only transmit 160 bits per second. I would like to show you this interesting picture. So famous American astronomer Carl Sagan asked NASA mission to turn the cameras from the outer space in and take a family portrait of the planets. Voyager 1 turned cameras towards the Earth and took 60 frames of the Earth and other planets. And from these 60 frames, it took, by the way, several months to transmit these frames. There was this famous photograph made that is called pale blue dot. And the Earth on this is less than a pixel in the size. So if you look at the size of the beam for the antenna, that antenna projects on the Earth, is that red area. If you think that the less than the pixel is the Earth, and that whole area where the signal transmitted and the data comes from, you can imagine how little power gets in the receiver. So that kind of tells you the challenges of the communicating from the far distances. So here's another example for the Optical program. So for the Optical program, NASA had designed unified S-band system, and that system was interesting in a way because it combined the voice, it combined telemetry, it combined the television signal in one radio link. This is an example from Apollo 11 mission. The video that was transmitted, it was 10 frames per second. I think it was 320 lines, slower rate video. And I would like to show you the video, historical video of the Neil Armstrong as he stepped.
That's one small step for man, one giant leap for mankind.
Can you guys decipher what he said? So this is the very first human stepped on the moon, and as he, let's go back. And as he was stepping down, he said this phrase. Who can say? Who can repeat? Okay, guys.
Something like one small step for man, a giant leap for mankind.
That's exactly right. So it's a very challenge. Like you can barely see that the lunar module and the Neil Armstrong is like that figure. You cannot really tell much from the picture. Yet we like that. This is like one of the most important steps in history of the human exploration of the space. So, of course, the Apollo mission was equipped with all sorts of cameras, and they were able to take, pictures of each other during the operations, close-up pictures, zoom-out pictures, pictures of space, pictures of Earthsat and everything. But all of that had to wait to come down to Earth for the astronauts' return. And so that brings us to the optical communication. And so my group is working on the optical and quantum communication. And the main benefits of it is that the optical terminal is small in size. So the telescope that we used on the Artemis mission was 10 centimeter aperture, which is about like 4 inches for those who are not metric. And you can use unregulated spectrum. So that is also a benefit. It can carry more data per bit, like it can carry per amount of power. And also it is using the narrow beam. So you don't have to have that much transmitted power because your power on the receiver the beam is more collimated, it's not spread out. And the question was, is it actually possible to do? And in 2013, our group, in collaboration with NASA, had demonstrated, yes, it is possible. Despite all the major challenges, there was a lunar laser communication demonstration. So the spacecraft went to the moon. It was called LADI. It was a lunar atmospheric dust explorer. And the mission was to study lunar exoatmosphere and some dust particles that they were collected. And this spacecraft carried optical payload on it. And for the duration of the mission, the team had demonstrated that they can not only establish link, but they also were able to transfer some scientific data. And everybody, like the whole world, could see that optical communication can be of great utility. So what are the difficulties? One of these difficulties is extreme pointing accuracy. So you need to be able from afar, like long range, point accurately at the ground terminal, and not only point, but also maintain the link. The atmosphere creates disturbance to the signal, it creates attenuation, so you need to be able to correct. And also the way it's usually addressed in optical terminals, that there are multiple ground terminals, and one of them will have a good weather. So again, the range is a challenge also for RF. So the delay, the time for the propagation is 1.3 seconds for the light to go from the moon to the Earth. Spacecraft moves. You need to build your hardware in a way that, when system is launched and flying and maneuvering, so it will be resilient to all these vibrations and contamination and radiation environment, temperature extremes, and all of that. That is a challenge. And so that was shown that the hybrid approach between the RF and optical will give you the best of both worlds. So this is a video example of, you can see here is that dot is the dome for the telescope for the ground station, White Sands ground station. I would like to show you the video, like a zoom out of that. Hold on a second. Yes. The reddish area is what laser beam covers on the Earth and how it looks from the lunar distance. So the spot is about 6 kilometers in size. And so you can imagine how challenging that engineering problem is, but it is solved. So that is what it is. So now I would like to tell you a little bit more about the Artemis mission. So NASA decided to go back to the moon, and the Artemis mission is aimed in multiple phases to achieve this goal. Artemis 1 mission was launched in November 2022, and the goal was to check for the SLS system, space launch system, the Orion capsule, the communication system, life support systems, all of that before astronauts can go on the moon. Artemis 2 mission, this is the mission that I was fortunate to be part of. This is the badge of the O2O, optical payload, was launched on April 1st, and it took 9 days. Artemis 3 mission is planned to be 27, 428. Artemis 3 mission is supposed to demonstrate the maneuvers. It's not going to go to the moon. But Artemis 4 is supposed to bring people on the surface of the moon. And Artemis 5 and so on, NASA is projecting to have sustained life on the moon, establish moon bases, and establish communications, and have a presence of people on the moon. So I was part, as I said, of Artemis 2 mission, and The Artemis 2 mission, this is the NASA picture of the NASA from the NASA website, and it shows different phases of the Artemis 2 mission. The first phase is to launch and be on low Earth orbit. There were several checkouts at this point, and I will show you more pictures about that, but at this point, when we were on low Earth orbit, our payload was activated. The next phase was going to the higher orbit, and when the spacecraft was in the higher orbit, they did several checkouts. One of the checkouts was that the astronauts took a manual control of the spacecraft, and they were able to do some maneuvers and everything. The very important check was where the spacecraft had solar panels, and the tip of the solar panels, there were multiple GoPros camera that could take imagery of the spacecraft itself, and these GoPros can turn and show sun, moon, spacecraft. But during the high orbit phase of the project, at this time, crew mission control decided they do survey of the spacecraft. They literally go and take a picture of every inch of the space capsule to make sure that the heat shield is not damaged, that the space capsule is intact and everything is looking normal. If there's somewhere they want to do close up, they do close up. And at that time, we were able to help to download some pictures of these GoPro cameras. So the next phase, after all checked out very well, the next phase was outbound to the moon, and the astronauts went for a several-day journey, day 5. After day 5, there was a flyby behind the moon where the spacecraft was not in the line of sight of the Earth, and there was about 40-minute break in the communication. And during that time, astronauts were actively taking pictures, so they had different, multiple sets of cameras. And I think there are, the schedule was such that 2 astronauts were taking pictures and 2 other astronauts were taking notes and handing out the SD cards and all the media and taking notes of what to do. And then later, they changed the roles. The other 2 started taking pictures, and then there was time. Then there was time to basically for them to take whatever pictures they wanted, and so there was structured science program, but then there was like a human curiosity type of picture. So this is the timeline on how we operated and how payload was operating. So day 1, activation, and from what I've heard, this is the very, we were able to establish a downlink to the White Sands ground terminal already in a few hours. So a few hours later, we were able to talk to the Table Mountain in California ground terminal, and we were able to download these camera survey pictures that were of a great utility. Everything in the timeline of spacecraft operation is very, very scheduled, very prescribed, and because the orbit is calculated, the amount of fuel, amount of life support, everything has to happen on time so that in a timely manner, and downloading this information in real time was critical to make decisions on time. So we've done, once communication was established and the Mission Control Center realized that they have this optical payload that can download gigabytes of data, science teams, like survey team, they all started asking for the optical communication payload. And at that time, NASA downloaded lots of pictures and started to release these pictures pretty much real time after review. So we were very thrilled about it, and that we can provide such an impact on the mission. Otherwise, all of this would have to wait until the mission is on Earth. But because of the optical payload, that was done pretty much real time. So I want to show a little bit of the slides about how the payload looks like and where it's mounted in the spacecraft. So you can see here, this is the Orion capsule. So on the top this is what's called the crew module. That's where astronauts. So our payload is mounted here. So there is a zoom out here. So this is the telescope that is latched in the position. There is a special latch assembly that holds it for flight and normal operation. It prevents contamination. It kind of keeps it safe when it's not needed. There is a controller box that was also designed by industry. And so the bottom part of the Orion capsule is the service module. This is where all the life support and everything. That is a picture of the Lincoln engineering team as we delivering the optical communication payload for the integration on the spacecraft. And so to give you perspective, so we've delivered in 2023, and the launch is 2026. So in this 3 years period of time, there was work going on for us to integrate with operations team, show them how to use our payload, for them to plan on how to use our payload and include us in the test activities and so forth, and also hardware verification and all of that. So here's the picture of the SLS rocket and the Orion on top of the SLS. And you can see, so that is where we are located. We are protected by the fairing ring. So we are at the bottom of the crew module. So, and the astronauts obviously sitting here in the capsule. And if you follow the events, it was scheduled, Artemis launch was scheduled early February, and it was rolled out, and there was some technical issues with, after wet dress rehearsal, there was some technical issues. And so eventually, we launched on April 1st. So this is the picture of the launch, and the whole mission was 9 days, and splashdown was on April 10. So this is the picture of the optical payload. We've asked the Mission Control Center to orient GoPro cameras to capture a video of our payload. And this is on a day one, when we are still in latched position. You can see, I'm gonna play the video. And this video is, hold on a second. Let me just mute it. So that is, how do I play the video? Oh, here you go. So this is, you can see how the latch assembly was released and the telescope opened up and started rotating to some, stable position. And of course, after 3 years being in latch position, everybody was so excited to be able to see that at least gimbal assembly, telescope, everything is working. And so this is the day one. When we didn't have to have like a line of sight of the ground terminal, at that moment what we did is just we make sure the gimbal, it can rotate in all the position in azimuth and elevation, make sure the star tracker is working. We checked all the optical alignment and make sure all the hardware is healthy and all of that. So this is another picture where the camera has a view of the Earth and our optical payload. So that is another picture. And for difference, I would like to show you. So usually when during the mission, NASA broadcast live stream to the YouTube, and people were able to see it. And whenever optical communication payload was up, they diverted the stream over the optical comm. And what I want to show you is here is that it's not. Here you go. It's too quick. How do I show it again? I'm trying. Maybe because of the pointer thing. Okay, because it has a pointer. Okay, let me play it again. So in the beginning it's S-band, and then up it changes to optical comm. And you can clearly see the difference, that the detail of the spacecraft. These are the thrusters that provide the stability. This is a little bit of the solar panel. Okay, so this is it. So this is a picture of the ground terminal in White Sands. This dome is optical terminal. These antennas are far behind and they're so much larger. So just picture doesn't show it that well. These are TDRS antennas. But the ground terminal for optical terminal looks like the four, let me get the pointer. The four smaller apertures are the transmitter, and two larger, four larger apertures is the receiver. So it's about 40 centimeter. Compare these two, 70-meter wide antenna. The TDRS antennas, I don't know, they're several meters also in diameter. So in that sense, you can tell that the efficiency of the receiver, of the optical receiver, is so much better. So then, as the mission was going on, we have downloaded all these cool pictures, and it's very rewarding to see that, that the work you do from the beginning of the project throughout the completion, delivery hardware, and actually see it work and do what it's supposed to do is very rewarding. And so this is our team. That includes NASA Goddard GSFC team and also Lincoln team. In the 9-day mission, we were able to download 474 gigabytes of data, many thousands pictures of images. So we also did the real-time 4K video with one of the astronauts, and it was interesting to see that the tracking algorithms in the hardware was able to support optical link through clouds, thin clouds, very low elevation angles, the crew exercise, burns, spacecraft maneuvers, and link was staying healthy and robust. And so that's an ultimate success for the optical comm, I can say. So that's the end of my talk, and do you guys have any questions?
Take some questions from the audience.
Hello, thank you for your speech. Could you talk a little bit more about your background and how you came to be where you are?
Oh, it's interesting. So I studied theoretical physics when I was in university, and then I worked in the experimental field for a long time. And so when I got to Lincoln Laboratory, I had worked in the industry. And so because of my background in physics and math, and my interest in computer science, so my role on this project is a software lead. So I wrote the software for the optical payload, and I think my skills as a physicist and as a software engineer kind of converged on this project, because that is a very interdisciplinary task to do. So if you're interested in something like that, learn how to program, study physics and math. So that's all it takes.
All right, we'll take another question from this side of the room.
Hello, thank you, Olga, for this amazing talk. It was really interesting to hear all how this communication works and how amazing and fast and optimal it all is. But talking about challenges that you mentioned, how are you dealing with For example, if there is something flying in space and blocks this laser view, maybe some particles or some meteor or whatever, something in space, is it gonna interrupt the laser communication? And how are you dealing with like some issues that can block the laser itself?
Okay.
Thank you.
I got the question. So the space is pretty empty, right? Despite the fact that we say the space is cluttered with all the spacecraft, but space is pretty empty anyhow. The challenge for this project was that when we mounted in the structure, so the field of view for the telescope, if you, for instance, change in azimuth angle and you start scanning, you see a little bit of different structure. So for the, or solar panel can block the view. And this is more, that was more kind of relevant for this particular project. And I think when we started the project, we had the mechanical model of a spacecraft, and we knew how we mounted on the spacecraft, and that mechanical model had provided us what is the field of view. So we had a pretty good analysis of what the field of view looking from a spacecraft will be like, and how the view of the telescope will be clipped, and what angles we're going to be blocked by structure or not. So that was it. Like in terms of like abstractions, what was interesting to me that we were able to track through the thin clouds. So in one of the terminals, the weather was not too good. It was humid. I think it was Australian terminal, and they have the most humidity. But you can see the thin clouds, and the way the system works is that it basically see loss of power in the tracking sensor, and will start immediately like search and pick up and find it. But this, because of the abstraction was so small, it was able to pick up in a fraction of a second. Like on the larger, how to say, in the larger picture, when you send Ethernet frames over the optical link, the frames are encoded in a way that it can withstand some loss of data. So you send some amount of data with redundancy, and the receiver receives not everything, but it receives portion of the data. But it's able to recover error-free because of the encoding algorithms on the link. So in general, it's very robust. I give you, design for it, which is
Great, thank you. Let's take a couple of online questions. Francesca?
Brielle, can you unmute and ask your question?
Okay, so first of all, I just want to say your work on the Artemis mission, it's very inspiring because I watched a splashdown before doing this program. Well, and I just found that it was just so inspiring to like, oh my gosh, I'm going to be working with people like along this, and to see someone, to actually be talking to someone right now who worked on it is just really, it's just really an honor.
Thank you.
My question is that I find a difference between analog and laser communication interesting. So I'm a big nerd over technological history, hence the reason why I have stuff like this. But I'm a big nerd, so could you explain the difference between analog and digital signals in terms of space travel? Thank you.
Yeah, so the beauty of the digital signal is that you are able to perform different data conditioning in order to transmit data error-free. With the analog signal, you send an analog signal and you receive it, and whatever you receive is there. So if you look like, I don't know, maybe it's the best picture, like when you have an older television with the analog signal, and you basically see missing pixels. Actually, like that, these pictures are analog pictures. Hold on a second.
Maybe one more Zoom question, and then we'll go back to the auditorium.
This is the analog picture. So you pretty much lose information. When you use digital encoding, so you have an ability to encode the data and process data. There is a technique called interleaver. Interleaving the data that you know what's your losses going to look like through the atmosphere, and you can encode data and spread the signal in time that you can reconstruct it later on error-free. And so in that sense, digital communication is more suitable for like lossy channels, I would say. So in that sense. Plus, you know, we wanted to transfer all forms of data. We want to transfer digital pictures. All the cameras are digital on board. The computers that the astronauts are using, they are just regular Windows computers. They had personal devices. All of this information and data are digital in nature. So there is not that many analog sources of information in there. So it's pretty much that the need for, I mean, I don't know, does it answer your question?
We're going to move to in-person questions.
Hi, thank you so much for your amazing presentation. I'm actually really into the Artemis missions. I even have my own zero gravity indicator plushie over here. So thank you so much for your presentation. I'm not too familiar with this whole communication with optics in the O2O system, so I would like to learn a little bit more. How does the data reach the ground terminal at the BWSI? And I also wonder, how do the astronauts interact with the systems to also pour their data in real time so NASA can receive it in the ground?
So the way the larger system is architected is that you have a network node on the spacecraft, and then there are multiple ground stations that the data get directly, but the ground stations are located in different locations. They are spread out across. One is in Australia, one is California, and so with that, then there is a network configuration, special network switch that goes to Houston, Houston has Johnson Space Center is a mission control center. All the data forwarded to the Houston center, and their operators can see the pictures and everything pretty much real time. The way astronauts, so it was interesting, the communication to the crew and to the mission control center is one form of communication is voice loops. And we had access for situational awareness to these voice loops, and we were able to listen on how astronauts talk to the flight director or science people and how decisions are made. And when astronauts wake up, mission control plays them a song, like wake up, so on. And then astronauts wake up, start telling jokes, and they have a little bit of private time. And then there are some cameras which are internal to the spacecraft, and these are streams that are sent automatically without astronauts doing anything. There are also camera streams from the GoPro cameras that are also streamed. Astronauts don't really do anything with that. And then the camera, the astronauts had different lenses and cameras on board to take the lunar imagery, and that was done with SD cards. And so that was a little bit surprising to me, but the whole process of taking picture, and at one point, a person from a science team asked astronauts to go through the pictures and pick the best 2 or 3 to get downloaded. And the astronauts said, I don't know, we've took 10,000 pictures. I don't know, how do I choose the best pictures? And I think what took, then he took SD card and put it in their personal computing device, I don't know, some sort of a computer, and then they transfer it over the network. And so there was a little bit of manual interaction. But all the computers on board were controllable and accessible by Mission Control Center, and the Mission Control Center can decide what to download, what's the priority, and they could tell, obviously there was not enough space on the hard drives there, and so at that point they would decide, oh, we've downloaded this portion of the data, let's clear this. And the astronauts pretty much didn't participate in that. So it was all done from the ground.
All right, let's do another question on this side of the room.
Good afternoon. Firstly, thank you very much for coming and speaking to us. This is an incredibly interesting talk, and really, I don't really deeply considered this side of the Artemis mission before, so it was very interesting to learn about. I would like to ask, though, I guess, especially since you mentioned that, like, specifically the optical systems were installed 3 years prior. I want to ask, I guess, what did your backup systems, if any, look like, or like backup backup algorithms that you had? What did they look like in case like something unexpected happened? And how do you keep what kind of maintenance is possible, if any, on these types of systems if they are to be disrupted at any point during the mission?
I may not fully understand you. Are you asking about the redundancy or how we design for resilience and redundancy? Yeah. So there are different approaches for life support systems and the payloads like optical communication, which is not considered critical. So for us, we want everything to work reliably. And so the constraints is will hardware survive radiation? Will hardware survive temperature extremes? And so the hardware is built and chosen particularly to withstand this temperature extreme, to withstand vacuum. And when we build the hardware, you choose components. You choose a particular way of laying out the boards. You choose a particular connectors. And then, so all of this process, when the whole assembly is together, it goes through the environmental testing, which we did in Lincoln Laboratory. So we have a special thermal vacuum chambers where you put the whole payload in, and so it creates vacuum and cycles temperature. And when it's all these extreme environments, we can then see how it performs. You know, we can see if it draws more power. We can see how sensitive is the receiver. We can basically monitor everything while it is there in the lab. And that gives us a confidence. There are certain standard like industry practices on how to design for space payload. For this particular space mission and for some other, because there are humans on board, there are more constraints on like mechanical aspects of it, which I'm not too familiar, but there is some regulations on fracture control, like, you know, if it breaks, so it doesn't, so the main thing, it doesn't damage the capsule, doesn't hurt astronauts. So this is the primary. But like, I cannot tell you much because I'm a software engineer about that, but most of the time, the redundancy is done by the hardware. So the software can also do different things and checks, but it's mostly checking how healthy is the memory, how healthy is the processor, is program loaded correctly, if I can move the gimbal to this angle or that angle and it responds properly. So this is the type of check the software does. But other than that, like there is always a risk that something will not work. And in the history of the space exploration, there are plenty of, you know, tragedies, and also something doesn't work, and that just comes with the nature of it. But we were fortunate; everything worked beautifully. So.
Francesca, maybe we can do another online question.
Nachiapan, can you unmute and ask your question?
Yeah. Hi. Thank you for talking to us today. It's not like every day when you get to meet somebody that actually worked on one of the Artemis missions. And my question was, like, how do you guys prevent any further data loss that happens during things like modulation or like during transit through the atmosphere? As I'm sure that there is a high chance of data being lost during those processes.
So this is more like a system level question. When the system is designed, the optical communication system is designed, we have a systems engineer who calculates what size of antenna, what power of a signal, what is the distance, and what is the loss through the atmosphere, and what is the loss. So there is a certain range of parameters that creates a link. And so we can say that that for a particular range, for the particular architecture of the transmitter and receiver, we can have that much, that much power in the signal. So this is all calculated before any hardware is designed. And at that stage, like an engineer, systems engineer will choose what type of modulation to use, what type of transmitter, what type of data rate could be supported. And you can see that the system optical communication payload can support different rates. And as we were going further and further in the distance, the ground terminals had to increase power so that the receiver was able to track it. So in a sense, you design system not for one operational point, but you design for a range of the optical powers. And as conditions change, you can choose between more power, different types of modulation, for instance, different data rate, you can encode data more, and such things that allows you for mitigation if your link somehow, not perfect, the atmosphere, like maybe when if it's too humid or too windy, or there some other impairment. But it's all physics. It's all calculated, so there are not that many surprises there. So
Awesome. Maybe one last question from the room.
Hi, so I just want to say thank you so much for speaking to us today. I just want to echo the thoughts of everybody. That's very, we really appreciate coming to speak with us, especially given your high stature. I want to ask, what is the professional opinion of these space agencies? Are aliens real?
what's the...
Are aliens real?
Aliens? I don't know. I guess it's a philosophical question. I think there is somewhere life beyond Earth. That's my personal opinion, not professional. I think the space is so vast, and maybe we are not ready as humans to see other civilizations yet. But I do believe that there is life somewhere beyond the Earth. Maybe it's far, 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 and so that's my belief. You have to believe in something, right? So.
All right. Let's thank our speaker one more time. And now I'd like to invite the students doing the t-shirt presentations to come on stage. Oh, online.
Good afternoon, Dr. Mikulina. It was really inspiring to hear from you today. My name is Gabrielle, and I'm a part of the Cyber Ops course. And I personally really enjoyed hearing about the Artemis missions and the brief history that you talked about for the human space exploration and your personal experience with the Artemis 2 mission.
Yeah, I'm Chase. I'm also from the Cyber Operations course. I just wanted to thank you very much for taking time to present this amazing work that you did with us. I was actually watching the live stream of the mission, and I appreciated all of the high quality footage that I was able to see thanks to 020. So I want to give you a personal thank you for that as well. But without further ado, we would like to present you with a thank you.
Guys, I think the camera is there for the... Thank you.
All right. Do we have any announcements?
So final event information will be sent out to you guys. Please be prepared to come on Saturday and then join us virtually on Sunday, as well as tomorrow we will have our BWSI alumni panel. So come with questions to ask your alumni about their experience and how it was after the program. So yeah, that's all from us. We will excuse you by class, and then you guys can head out for the day. So race cars will excuse you guys first. Please use the door to your right.
Thank you.